In this video, we're going to start looking at and solving systems of equations. Now, I've condensed 5.1 and 5.2 down into one single video, specifically because the graphical portion of this we've already done a whole bunch of in Chapter 4, so I don't want to spend a ton of time going through that, but I do want to spend at least an opportunity to show where the graphical and algebraic representations of these things cross over and we see the similarities there. So if you're watching this, 5.1 is solving it graphically, 5.2 is doing it algebraically. But overall, let's start with our core bare-bones definitions of systems of equations and how do we solve them. So a solution to a system of equations is where two lines intersect or cross each other. A system of equations is where I have two or more equations set up and I'm comparing information and things about them. In this case, where do these two things intersect one another? Now, if we're going about this, we want to try and be as exact and precise as we possibly can be and make sure that we determine the exact point on both of those graphs. Some people will just solve for a point on one graph, and that isn't necessarily the point where both graphs cross one another. So we essentially solve for a point at random, and then it ends up not being the thing that we need between them, the information given to us. So we're going to go through two methods with this, the graphical and algebraic methods. Graphically, our process is listed right here. We're going to graph the two equations on a given set of axes. That's using a lot of the Chapter 4 material, so go back and reference that as much as you need to. Once we have graphed those things, we then determine by inspection, meaning just take a look at the graph, and where the two lines intersect each other, and we write that point down as the final answer. A bulk of the time spent doing it graphically is actually just setting up the graphs and looking at what I've been given. After we actually have those, you're going to look at it and go, oh, bam, point to it, there's the spot, we have our final answer. Now, the warning I will give about doing this graphically, and if we are given something and we're told to solve it graphically, if you have to guess this point based on the graph, then this method is not recommended. Meaning, if we have to look at a graph and say, okay, right at this point, it looks like it's either like a 2.7, 2.8 for an x value, and maybe for the y value, it's like negative, 6.3, 6.25, something around there. When we have to guess at what the point is just by looking at a graph, I recommend not using the graphical strategy. Only because that can cause us to get incorrect guesses, and we don't want to do that if we possibly can. The algebraic method that we're going to go through is a bit more exact with finding that answer. So in 5.2, we cover an algebraic method here known as the substitution method. We're going to go through another algebraic method in 5.3, but this is our first one that we're going to take a look at. And I do have the process written down here, as I recommend pausing the video and writing that down for yourself and referencing that as necessary, because we are going to use this as we go through these problems. So first and foremost, solve one of the equations for either variable, meaning I'm going to solve for x or I'm going to solve for y in the first or the second equation. It doesn't matter which variable you pick, it doesn't matter which equation you pick one and commit to it. We then substitute the rewritten equation from step 1 into the other equation for that corresponding variable. So if I solved for y in my first step, I'm going to plug that equation that I found in for y in my second step. This should result in an equation that contains only one variable, and this is the kicker right here. I cannot solve an equation with two variables and get a single number answer. If I have an equation with one variable in it, then I absolutely can get a single number answer there. After that, Step 3, we're solving the resulting equation algebraically. We go through and we find y equals a number or x equals a number. Great, we have half of our answer. We then substitute the result that we found in step 3 into one of the original equations to find the other variable. This is another step where it does not matter which of the original equations you choose, just pick one and commit to it. Last but not least, and this is especially the case if you are in my class and you are taking some notes on this and trying to figure out what am I looking for final answers, write the solution as an ordered pair. Here's my input value, here's my output value. On a test, I am expecting you to have something written like this. We have some number here and then some number here in an ordered pair form like this. Sometimes they don't want that for different online programs, and fine, let that be what it is. On the tests in my class, I am looking for an ordered pair final answer. Now once we have that ordered pair, if you would like to do step 6, we plug this ordered pair back into each original equation and check to make sure that both sides are equal to one another. That's how we know we have the correct final answer, and we're good to go from there. Now our last notes before we take a look at 4 examples with this, we can and will have different numbers of solutions based on the equations that have been given to us. So we can have parallel lines showing up, meaning we have no solution. We can have two equations be the exact same line and result in there being infinite solutions because they intersect or touch each other at all points. And we can have our final situation, instances where the equations are neither parallel nor the same line. And this is where we get a single solution to the system of equations. And this is our most common occurrence here. We get something like this showing up. It's at this one point that they cross. Now we're going to take a look at our 4 examples down here. I am going to show the first one using a graph and how we can solve that, but the other 3 I am then going to go through and solve algebraically, just so we can see what these things look like graphically and visually, and then also just with numbers afterwards. So let's jump on over and get that going now. Looking at our first example, we've been given the 2 equations, x plus 3y equals 10 in red, depicted here, and 4x plus y equals 18, depicted in blue, right here. Now I'm trying to solve for the solution to the system of equations, meaning I'm trying to find where do these 2 things cross each other somewhere on this graph. So I've taken the liberty of using Desmos.com to type these equations in, and then just auto-displayed these for me. I would recommend that if you have not used it before, I'm going to write it down here above the graph. Desmos.com is a fantastic tool that we can use for graphing things. So I have my graphs. Where do these things cross each other? Well, they cross right at this point. What is that value? I'm going to put a little black dot there. So what's the x value? Looks like it's 4. The y value looks like it's 2. So my final answer for the point of intersection is going to be 4, 2. Now again, I've kind of skipped the setup steps for how do we set up our set of axes and graph these things, but that is using all of the chapter 4 material, and I would recommend that you go back and view those notes if you are asked to solve something like this graphically on your homework or on a test or anything like that. Looking at our second problem, we're given the equation negative 2x plus y equals negative 11, and x plus 3y equals 9. Now we're going to solve this one and our remaining examples using the substitution method and going through this algebraically. So our first step says to solve one of the equations for either variable. So I need to solve this first equation for x or y, or the second equation for x or y. It really, truly does not matter which variable in which equation you choose. Any of the options available to you will get you to your final answer. Just pick one and commit to it. Some are going to be a little bit easier in terms of getting them by themselves. Some will be a little bit harder, but they will all work. So I'm electing to choose, I want to solve for y in the first equation. Y is kind of already by itself right here in this term. There's nothing multiplying to it. So all I would need to do is add 2x to this side and this side of the equation to get it by itself. So the result of that would be y equals 2x minus 11. So that's our first step. Step 2 says to substitute the rewritten equation from step 1, right here, into the other equation for that corresponding variable. Okay, so that means this is going to get plugged into equation 2 here. Some people like to write, I forgot to do this, some people like to write just off to the side equation 1 and equation 2 for themselves, because that can be helpful with labeling. So my second equation, I am now going to substitute in for y 2x minus 11. When you are doing this step and writing it out, please, 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 for your own sake and your grade, actually take a line to write it out like this. Looking ahead, you might notice, yeah, 3 is going to multiply here and 3 is going to multiply here, and I'm going to get answers, and you might know what those answers are, and that's awesome. I have seen way too many people correctly identify that I'm going to use the distributive property and then only multiply, let's say, 3 times 2, and they completely forget about the minus 11 in there. So take one line, write the whole thing out, you know what's going to come next, and that's awesome, but establish where you're at first and then go through that. And step 3 would tell us solve the resulting equation algebraically, so I'm now just going to solve this thing for x. Fantastic. So now I have solved this thing for x. I have half of my final answer. Remember, we want an x and a y value. So next, I'm told, this is in step 4, substitute the result from step 3 into one of the original equations to find the other variable. So I'm going to take this 6 equaling x, and I'm going to plug that in for x in either the first equation or the second equation. Again, it does not matter which one you choose, but it has to be one of our original equations that we have here. I'm going to, I'm just going to plug it into equation 2 because why not? You could try plugging it into equation 1 if you'd like to. I'm going to make a note that I'm using equation 2. I'm substituting that inside of parentheses, and again, anytime you do substitution, I recommend taking one line just to write that out for yourself before you do any other kind of operations there. And always substitute inside of parentheses here. So let's go ahead and we'll solve this thing for y. And now that we have our y value equaling 1, we have our x, we have our y, we can take the final step to rewrite this as an ordered pair, 6, 1, and there we have our final answer. Be sure to double check with your instructor if they are fine with you leaving your answer in this form or if they want it as an ordered pair. I am letting you know that if you are one of my students in my class, I am looking for the ordered pair final answer on all of these problems. Love seeing all of this work. This is great, but I need an ordered pair. We're told to find the solution, and the solution is an ordered pair, so we need to make sure we're giving that in its correct final form. In our third problem, we've been given the equations 5x minus 2y equals negative 10 and y equals 5 over 2 times x. So we're going to, again, go back to our algebraic method, the substitution method, to go and find our answer for this. The first step, solve one of the equations for one variable. I want the first one or the second one solved for x or y. Y equals x equals, that's my goal with it. Now thankfully, my second equation looks like it's already been solved for y. I have y equals 5 over 2x, so y is already by itself. It's been solved for y. Great, the first step is done for me. My second step says to substitute the rewritten equation from step 1, or given equation here, in for that corresponding variable in the other equation. So I can go ahead and just plug this in. So wherever there was a y showing up in here, I'm going to replace that with parentheses 5 over 2x. Now that that has been substituted in, I can go through and I can solve this thing for x. And now I'm getting something weird showing up. I have these things subtract. I get 0 times x, which is just 0. Anything times 0 is 0. So I get this weird statement showing up here, 0 equals negative 10. If we think back to earlier in the quarter when we had weird things like this showing up, what did this mean with the equation that we were working with? It meant that there was no solution to this, and we can have that show up with these problems just like we did in the past. So at this point in time, we can stop entirely and we can write out for ourselves no solution, and we are done with this problem. I will note that some online programs will not give you the option to write in no solution. Some programs will prefer you to write DNE does not exist or something similar to that. If you are in my class and you are trying to figure out what I'm looking for our final answer here, no solution works great from here. This is a perfectly acceptable and desired final answer for a problem like this. And now at example 4, our final example for this video, we've been given the system of equations 2x minus 3y equals 12 and negative 12y plus 8x equals 48. So with this, we have the choice again to either solve the first or the second equation for x or y. Really doesn't matter which one we pick, really doesn't matter which variable we pick. We just need to pick something and commit to it. I'm going to, I'm going to go switch it up a little bit. I'm going to solve the second equation. I'm going to solve it for x here. So if I wanted to do that, I can make a quick note down below. Let's write that out. I'm going to solve this second equation for x. Okay, so I'm going to try and get x all by itself on the left side of this equation here. Okay, so we solved this second equation for x. We use the 2.6 material, solving for a specific variable to make that happen. Reference that if you need to. Just put a little note here. This is the 2.6 process. So I solved my equation for one of the variables. Let's make this a more accurate y. There we go. Now, I'm taking this thing that I found from my second equation, and I'm substituting that in to my first equation. So wherever there's an x, I'm going to replace it with this 3 over 2y plus 6, and then I'm going to solve the resulting equation for y. And here, I'm getting another weird situation showing up. I have my variables all canceling out. Actually, I put an extra x in there. Okay, now they actually accurately cancel out. And now, when we do this, we notice, okay, these two sides are the exact same thing. They are identical to one another, which tells me I can stop here, and how many solutions am I going to have? I'm going to have infinite solutions. And I could just write that in. as my final answer and call it good there. So all that stuff from, I believe it was the 2.4 material where we had one solution, infinite solutions, or no solutions can all come back with this stuff as well. As a quick recap of what we covered, we started working with solving systems of equations. We went through how to solve them graphically and how to solve them algebraically. Remember that at the end of the day, we are looking to try and find where do the two lines intersect or cross one another. So we had our two methods here. Graphically, we are going to use a lot of our Chapter 4 materials, so reference back to that as much as you need to. And we don't really want to use the graphing method if we're going to get some non-integer answers, 3.7, -5.1, things like that. The substitution method that we have right here, this is the main stuff that we want to have nailed down and use for these types of problems. Note also that we could have parallel, same lines, and neither parallel or perpendicular or parallel lines, meaning we can have no solutions, infinite solutions, and one solution showing up just like we saw with our previous material. And then we had 4 examples that we went through here. And I'm going to give you guys the opportunity. I do have some extra practice problems here. I'm going to go ahead and jump us over to that screen. So here's a solid starting list of a whole bunch of practice problems that you could try using the substitution method for to get to your final answer. I'd recommend pausing the video here if you wanted to go through and solve any of these. And I'll go ahead and jump us over to the answer key here now. The answers to the problems that were previously on the screen start right here at 11 and they move down accordingly. Hopefully you got a good chunk of those right. If you got any of them wrong, that's okay. Go back and find where the error showed up. It's generally a silly little negative sign showing up in there somewhere, screwing things up like it normally does. But that's everything for our introduction to the 5.1 and 5.2 material.